The second one is what we call angular speed. And the third one is the unit circle. Okay, unit circle, very important, which is why we're going to actually spend the whole next class on it as well. The next class that we learn in material. So first thing we're going to look at is arc length. So arc length basically measures how long part of the circumference of a circle is. Okay, so when you're thinking about an arc is a part of the circle. And when you draw an arc, the way it's made is you put an angle inside a circle, like this, and the two rays of the angle come out and hit the edge of the circle in two spots. If you connect those two spots, you get an arc. Now, if you double the size of this angle, what do you think would happen to the size of this arc? Yeah, you would double the size of the arc. So for example, if you had a 90-degree angle, that's almost 90. But if you had exactly 90, that would give you a quarter of an arc, quarter of a circumference. If you made this angle 180, then it would give you half of the circle, half of the circumference. So the arc size and the angle size are directly proportional. If you make the angle half as big, then you make the arc half as big. If you make the angle 5 times as big, you make the arc 5 times as big. They're directly connected. And because they are proportional, what that means is we can set up a proportion to make an equation to find arc length. The key when you set up a proportion is one side is what you already know. It has to be a fact that's true. And the other side is what you're trying to find out. So let's think about like converting feet to inches.
Oh, sweet geometry.
So feet, inches, One side has to be something you already know is true. It can be anything that's true. Doesn't matter. But what is something that is true that connects feet to inches? 1 foot equals 12 inches. Now she specifically put a 1 here and a 12 here. Does that mean I can only put certain numbers on that side? Like could I only put a 1 here? No. I could put any number that I want. I could put 8 and then I could put my variable in the bottom. The key is these two numbers are something that is true. She could have done a 2 and a 24. That's also true. But a lot of times we use 1. So let's see if we can set up a proportion for this. So what I've drawn here is 2 angles and 2 arcs. I have my first angle is theta. Then I do another angle, theta 1. I have arc S, that's an S, and then arc S1. So let's start by writing down a proportion, kind of like I did for feet and inches. These are going to be the 4 things that are going to go in my proportion. One side is going to be something I know that is true. The other side is going to be my variables, what I'm trying to figure out. For now, let's just plug all these in as variables. Just like I did on this one, I wrote feet, inches first. So let's start with that. Anyone think they could tell me what I could put on the left-hand side? Don't worry about writing any numbers yet. Okay, we could do the arc is to the angle as what would have to go on the other side now.
The arc is to the angle.
The arc is to the angle for the other one. Now that by itself, that's pretty useless. We don't have any numbers in it. We have to fill in one side with a fact that we know. We're going to do it on the right. And there's a fact we talked about last time when we started learning about radians. That, let me just erase these circles so it's a little easier to see. If this angle is 1 radian, this angle right there, then it automatically makes the arc the same size as something else in the circle. Does anybody remember? If this angle is 1 radian, then this arc is exactly as long as something else, as the radius. And that's the fact that we can use. That's going to be like my 1 foot, 12 inches. There's my true fact. If you have an angle of 1 radian, it automatically makes the arc equal to the radius. And you will know the radius in the problem. So that'll be a number. So now, you know what? I'm just going to put that in. Well, I'll just write it again. You probably have more room below. So change S1 to R and change theta 1 to 1. And the goal is to find a formula for the arc length, which is S. So how do you solve a proportion? Remember? Yeah, you cross multiply. What's S times 1? S. And what's R times theta? R theta. There you go. And that's the formula for the length of an arc. It's S equals R theta. And I could have done the same thing with the feet and inches. Like if I had 12 feet, 12 inches in 1 foot equals X inches in Y feet. You can cross multiply to come up with a formula. So you could say something like 12y equals X. 12 times Y, and then 1 times X. So this tells me that if I want to convert Y feet into X inches, I just take the number of feet and multiply by 12. So there's the formula written as an equation. And I just did exactly the same thing right here. S equals R theta. So the formula has 3 variables in it. The first one is S, that's your arc length. R is your radius. And theta is your angle. But we have to be careful about the units. When we came up with a true fact between angle size and arc size, we used a fact based on radian measurement. So that means this entire formula is based off using radians. So if we have an angle that they give us that's not in radians, the first step is to change it to radians. And they can really ask 3 different kinds of problems. Find the arc length, find the radius, or find the angle. They'll give you 2 out of 3 of the variables. Okay. Everybody have the formula? Okay. You don't really need a picture here. The sentence up above is enough. But it says find the length of the arc, where the radius is 2, and the angle is pi over 4. So, Layla, what's my formula for finding the length of the arc? S equals R theta. And Caleb, can you tell me one piece of information that they give me and where it would go?
Radius
radius is 2. What about the pi over 4?
That would be
Theta. Yep. So pi over 4. So my arc length is equal to 2 pi over 4. And what does 2 pi over 4 reduce to? Pi over 2. And what did we just find?
The arc length.
Arc length. So what do you think my label should be?
Inches.
In this problem, length is measured in inches. So you could divide that out and get about 1.57 inches. Or just leave it as pi over 2 if they don't say you have to write a decimal. Any question on it? Right, let's try one a little different.
Are we going to be converting degrees to radians? Okay, yeah.
So this one says find the radius if we know the arc length is 3 pi and the angle is 60 degrees. Well, we can start with the formula. What's my formula that connects radius, angle, and arc? S equals r theta. But before we start plugging into it, we want to be careful. What do I have to be careful about?
That 60 degrees is not in radians.
Right, this 60 degrees is not in radians. So, does anybody remember, what do we multiply by
To get to radians?
to get to radians?
I do.
Yep, I'm going to multiply, I'm just going to put that right here, times pi over 180. And as an exact answer, what do I end up with when I convert that? Yeah. Pi over 3. So pi over 3 is my what?
R. Oh, yeah.
No, not my r.
Okay, not theta.
We're going to find the r.
Yeah, theta.
It's my theta. And what about my s? The arc length is 3 pi. So 3 pi equals r times pi over 3. How are we going to move the pi over 3? We can move both of the top and the bottom to the other side at the same time. How would we do that? Yep. Divide each side by pi over 3, which is the same as multiplying by 3 over pi. So, yeah, we said divide by pi over 3, which is the same as multiplying by 3 over pi. That's gone. And that's gone. So what do we get for a radius? 9. Not inches. Feet. 9 feet. So if you're ever solving for S, that's a length. If you're solving for R, that's a length. If you're solving for theta, that's an angle. Notice they don't write RAD, or I didn't write RAD after the angle, because RAD is a unit where we know it's radians if you don't see the little degree circle. So any questions on how to find arc, either from a sentence, or if I just gave you a picture like that and said solve for S? And that's what you saw similar to on the last test.
So if we didn't have the formula, how are we supposed to figure that?
You could figure it out like as a percentage. If you know you had an angle that was, say, 90 degrees, then you know 90 out of 360 is 25% of the circumference. So you'd have to know the circumference formula.
Wait, did they give the full circumference of the circle in that example?
In the problem in the, yeah, because they told you the radius of the circle, so you could find the circumference.
Okay.
Yep. And if you know the whole circumference, you could think about the angle as a percentage.
I see. Jeez.
But this is simpler. You don't have to think about percents.
Yeah.
You just S equals R theta, plug it in, and you're good. All right, so second topic. So angular speed or angular velocity. The idea with angular velocity is it's used to measure something spinning.
Spin.
Yep, something spinning. So you can call it angular speed or angular velocity. This is different than the kind of speed you measure like with a car. Right? That's linear speed. It's moving like on a straight line. Angular speed is something you'd see like if you have like certain power tools. Right? You may have like a Dremel. It's a power tool that spins. And it may spin at like 10,000 RPMs. 10,000 revolutions per minute. So it's measuring how fast it's spinning. And the reason why we have angular speed is because if you try to measure the speed of something spinning and you don't use angular speed, weird things start to happen. Does anyone remember what the formula is for just regular linear speed? It starts out with distance equals.
Yeah, I need to know.
Rate times time.
Rate times time. So what's rate equal to?
Rate is equal to distance divided by time.
Distance divided by time. Okay. So let's keep in mind that if you take how far something moves divided by the time that it took, that will tell you the speed of the object. So I've got a circle. I've got 3 dots on the circle. I'm going to make 1 revolution of that circle, and I want you to focus on what happens to the dots. Let me, let's make one of the dots green. Let's make that one green. All right, let's see if I group that, if it all stays together. All right, so as I spin it around 1 time, okay, make 1 full revolution, each dot traveled as I did that. Did all the dots travel the same distance? No. Which one traveled the farthest? Right, the green one traveled the farthest, the red one the second farthest, and if the black one was exactly in the center, then it wouldn't have moved at all. Now, if you compare the amount of time it took for the green one to travel, the red one to travel, and the black one to travel, how do the times compare?
They're all the same.
They were all the same. So the times were all the same, but the distances were all different. So what does that mean about each dot if you try to describe it with this formula?
They're gonna have a different rate.
A different rate, yes. Each dot is traveling at a different speed, if you think about it linearly. So what we do, instead of thinking about it spinning and thinking about it linear, like in a linear way, we're going to think about it as saying all those dots made 1 revolution and maybe it took 3 seconds to go all the way around. Yes, size of the revolution is different, but if we just say they all are traveling at 1 revolution every 3 seconds, then they all have the same angular speed. Any question on that idea? Okay, so that's where angular speed kind of comes up. The kind of the default unit that we will always use is radians per time unit. Because you can measure the speed of something spinning in lots of different units. I would say revolutions is pretty common, like revolutions per minute, probably the one you might be most familiar with. But in our book, if you ever see a question that says, find the angular speed, and they don't say what unit to use radians. What time unit? I don't care. Whatever time unit's in the problem. Radians per second, per minute, per day. Time unit doesn't matter. So linear speed, that would use units that measure in a straight line, right? Radians, degrees, and revolutions, that measures something spinning on a circle. How much of a circle did you complete? Feet would never be used to measure, like if you had a ruler, think about it, it's straight. So you're measuring something from point A to point B. Same with like miles and kilometers. Those are straight line units. Time units can vary, feet per second, that's pretty common, miles per hour. Generally, we write speeds like this, but there are some that you can use a 3-letter abbreviation, like MPH. That would be miles per hour. Or RPMs is usually revolutions per minute. But other than that, like they don't, I mean, I guess you could say FPS, but then you start getting a little confusing, like, is that frames per second, or it's normally feet per second? So if you're not sure if you should use a 3-letter abbreviation, just write like miles/hours, miles per hour. So we can come up with all kinds of formulas to try to convert between angular velocity and linear velocity. But the easiest way to do it is the same way I taught you how to change between degrees and radians. You know the conversion between degrees and radians. It's a 180 and it's a pi. You just have to figure out if the pi goes in the top or the 180 goes in the top. As long as we know conversions, and you are expected to know simple ones like feet to inches, inches to yards, what else? Minutes to seconds, seconds to hours, hours to days, things like that. But as long as you know those basic conversions, all we have to do is figure out, should the number go in the top or the bottom? And we'll figure it out based on the unit or the dimension that we're trying to get in the problem. So we're going to start out a very straightforward one. This number is not even a rate.
All right, is
This number
this
is,
dimensional analysis?
Yep.
Just an example.
Yep. So we're not even doing a speed yet. We're just doing kind of half of the speed. We're just doing the time part of speed. So 3 days. What we're going to do is we're going to end up writing a series of fractions.
This just looks like trigonometry.
So we want to convert days to minutes, and we're going to do it 1 unit at a time, because I don't know how many minutes in a day off the top of my head. But I do know how many hours in a day, and that'll get me 1 step closer to minutes. So what's the connection between days and hours? 24 hours in 1 day. We're trying to get days to cancel so we can get to minutes. Days is in the top. Where would days go over here? But so we're going to put day, hour. There's 24 hours in 1 day. And now if you multiplied that out, you would have hours. Now we want hours to cancel, because we're trying to get down to minutes. Where would hours go this time? Bottom. Minutes would go in the top. And what's the connection between minutes and hours? 60 minutes in an hour. You could also write 120 minutes in 2 hours. It's more complicated, but you could, any fact that you know is true, you can fill in right there. Hours in the top, hours in the bottom. And now multiply straight across. So 3 times 60 is 180 times 24. 180 times 24 gives me 4,320 minutes. Now that's not minutes, that's not like minutes, or minutes per, with a time, with a distance in it. It's just minutes. It's not feet per minute or seconds per minute, it's just minutes. Any question on that? Okay. Now let's try a speed. 50 feet per second. So now you're dealing with 2 units, feet and seconds. And we want the length unit to be converted to miles and the time unit to be converted to hours. And we do each one separate. So 50 feet per second means you're traveling 50 feet in 1 second. What part of the rate do you want to work with first, the feet or the seconds? Seconds? Okay, so we need to get seconds to hours. Where would seconds go to cancel out where it is now? Top. And what's the next unit up from a second? Minute. And the connection between minutes and seconds? 1 minute. So now you have feet per minute. Okay, let's keep going. Where would minutes go this time? Top. And what would go in the bottom? And the connection? 60 minutes in an hour. Now you have feet per hour. Now the last unit we want to get rid of is feet. So where would feet go? Bottom. And miles would go in the top. And what's the connection between feet and miles?
It's 5,280
Yep. What? 5,280
feet in 1 mile.
feet in 1 mile. So now we multiply straight across. And that will give us our answer. All right, see what we get. So 50 times 60 times another 60. That gives me 180,000 in the numerator. And divide that with 5,280. So that's 34.09 miles per hour. Okay, so that was a rate. And the point of that is just to get used to dimensional analysis with units you're comfortable with. Now, we're going to try it with units you might not be as comfortable with. 200 radians per second. That's per 1 second. Okay. We can really start any way we want. So anyone think they could tell me my first thing I want to try to do?
Convert radians to revolutions.
Okay, let's get radians to revolutions. So where would radians go? Bottom. This is not normally something you would do. Most of the time, you want radians. You do not want, well, it depends on what you want to do, I guess. So I take that back. But radians is a lot of times the unit that we want. All right, how many radians in a revolution?
1. No, 2.
Well, how many degrees in a revolution? 360. So how many radians in 360 degrees? 2 pi. So there are 2 pi radians in 1 revolution. That was the only thing that was really the little bit more difficult part. Now the time unit we've already done. 60 seconds in 1 minute. So it's, actually I can reduce that if I want first. So it's 100 times 60, which is 6,000, divided by pi. So 6,000 divided by pi, 1,909.9 revolutions per minute. Any question on
I
that?
got a different answer from not simplifying.
I might have messed up. Did I mess up simplifying?
What did we have done?
So if you didn't simplify, it's 200
Oh,
You didn't simplify the 60.
times 60.
You didn't simplify the 60, that one you changed.
You don't have to. Divided by 2 pi. Wait a minute, what did I do? So I divided the 2 into 200 and it went in.
And how about the 60 that's on the top?
Well, you can't divide it into both. Because it's not addition, it's multiplication. So like if you had 8 times 12 divided by 2, you don't divide 2 into 8 and 2 into 12. You just divide 2 into the 8 and say 4. So let me just see if
They shouldn't be that far off, I don't think.
I must have just put something in wrong. So if you reduced it by 2, 2 goes into 200 100 times. So that's 100 times 60. 100 times 60, that's 6,000. And then divided by pi. So there's that one.
Oh.
Must have been my parentheses. I think it's order of operations. Let's do 200 times 60 divided by 2 pi. Yeah, it was my order of operations.
Oh, so it'd be like divided by 2 times pi.
Yeah, it must have done the divided by 2 first, the other case, and then multiplied that answer by 3.14, which isn't what I wanted. So it is 1,909.9. Any question on that one? So far, when we've dealt with the speed, we changed linear to linear. Feet per second, miles per hour, 2 different ways of doing linear. Radians per second, revolutions per minute, 2 different ways of doing angular to angular. Now, what we're going to do now is look at how we can take angular and change it to linear. So now we're going to jump from one type of speed to another. The first part of this question said to convert revolutions per minute to radians per second. Well, we just did that. We just did a conversion between revolutions per minute and radians per second. Okay, so we basically already did that type. But what we haven't done is find the linear speed. So the idea here, if you want to kind of imagine what's happening, you've got a wheel spinning at 1850 RPM. If that wheel was spinning in the air, and all of a sudden it made contact with the ground, and it just took off straight, we're basically figuring out how fast it would be going.
For the entire time or for...
Well, we'll assume that it never slowed down.
Okay.
But yeah, instantly when it hit the ground, what would be its instant speed before it starts slowing down? Or another way you can think about it is if you had a string and you had a weight on the end of it, and that string was spinning around, and the string was 18 inches long, and all of a sudden you were spinning and you let the string go. That weight would take off, right? It would go in a straight direction. How fast would it be going if you let it go? That's the same exact problem as this. So anytime that we want to convert from linear to angular, or angular to linear, revolutions is the unit you want to be in, okay? Which we already are. So part A of this problem wouldn't have even helped us to do part B. It was unnecessary. It was just practice between radians per minute and revolutions and radians. That's it. So let's write down what we have. 1850 revolutions per minute. Well, let's get the time unit out of the way first. How would I get minutes to seconds?
5 by 60 or multiply by 11.
Yeah, in 1 minute, there are 60 seconds. You basically divide by 60. Now that's revolutions per second. Now, we're trying to get rid of revolutions. The unit that we want is feet. So where would revolutions go to cancel out? Would go in the bottom, and feet would go in the top. We need to figure this out. How many feet in a revolution? That's not like me asking you how many inches in a foot. There's always 12 inches in a foot. But how many feet in a revolution? Well, it depends on, specific to the example. It depends on the size of the revolution. Is it small or is it big? Well, we have a tire that has a radius of 18 inches. So here's your tire. That's 18 inches, which is what in feet?
1.5.
Yeah, we might as well change that to 1.5 feet. And I want to figure out how many feet in one revolution of that tire. So one way to think about it is if you put the tire on the ground, and you mark a spot on the tire, and you roll the tire along the ground until that mark is back on the ground again. However far the tire rolled is one revolution. Or, if we don't physically have the tire to do it that way, one revolution of the tire is really the what of the tire? It's the circumference. So the circumference formula is how you jump from revolutions to linear. What's my radius in this case? 1.5. So what's the circumference of this tire as an exact answer?
3 times 5.
3 times pi, and what's my unit on that? Feet. So it's 3 pi feet. And that's the number of feet that is in what?
1 rotation slash the circumference.
So one
One revolution.
revolution, yes.
Yeah, that's what I meant.
So in this case, there are 3 pi feet in one revolution. You have to figure that conversion out every time. It's not one you can memorize. And now, revolutions is gone. So we can multiply it and see what we get. So 1850 times 3 pi. And what are we dividing by? Just 60.
Oh, never mind.
So that's 290.6 feet per second. Any question on that? Jumping from angular to linear.
What did you get as a final answer?
290.6. The way to always do it is to make sure you are in revolutions. And then use the circumference formula to find out how big one circumference or one revolution is.
So 1 revolution equals the circumference.
Yes, 1 revolution equals the circumference. Another way to imagine it is pretend like this was a piece of string, and you cut it, and then you laid it out flat. That's what we're finding. So any questions on that? All right, so that was the second topic. So first thing we looked at was arc length. The second thing was the angular speed. And the last thing is the unit circle.
Oh wait, so this is a different field.
Yep, it's part of yeah, part of what we're doing, we're not going to do the whole thing. If we finish it today, that's good. If we don't, plenty of time to finish tomorrow. But I think this is, in terms of like the arithmetic, this is easier than the angular and linear velocities. It's much easier. You can do all the arithmetic in your head for this. Yeah. All right, so 6.2 is on what we call the unit circle. We talked about a unit circle before. It's just a circle that's a special size. Does anybody remember what the size of it is?
The radius is 1 radius.
The radius is what?
That is 1.
1. Yeah, 1 unit. Foot, 1 inch, doesn't matter. That's my unit circle. Alright, so what I'm drawing here is I'll just erase it. XY axis. And I have a circle with the center of the XY axis should be in the center of the circle. And this is the whole idea of unit circle trig. So somebody give me an angle between 0 and 180.
72.
72. Okay. So if I start here, 72, that might be up around there, like that. The point is, when you make an angle, it doesn't matter what the degree is, 72, 106, negative 408, doesn't matter. When you draw an angle on a circle, the terminal side is going to come out from the center, and it's going to hit the edge of the circle somewhere. The whole goal of unit circle trig is to figure out what the coordinate is of that red dot. That's the whole goal. Now, 72 would not be one we could do. We're going to be able to do ones that are multiples of 30 and 45.
Why 30?
You'll see why. The quick reason why we can do 30s and 45s is because there's special right triangles called the 30, 60, 90. And there's another special right triangle for the 45, 45, 90.
Oh, yeah, that's right.
There is no really special right triangle for the 72, 18, 90.
Yeah.
Nobody knows that. So we're going to be able to do the two that are well known. 30, 60, 90, 45, 45, 90. So this is summarizing exactly what I just said.
Yeah.
So for certain angles, and by certain I mean multiples of 30 or 45, technically we can do the 15s. You might be like, wait, there's no 15, 75, 90 triangle. People know. There isn't, but there's a way to do it when we learn something else later on. So for now, 30 and 45. And I mean all the 30s and 45s. 135, 225, 315. All multiples of 45. You can sketch that angle in a circle.
Sorry, what did you say that the upwards most side of the angle was called again?
Terminal?
Terminal.
Yeah. So when you sketch an angle in a circle, you don't have to worry about the arc length. The idea is you have an initial side and a terminal side. And the end point of the terminal side, which is also the end point of an arc, if you drew it just like that to kind of connect it back with what we just learned a little bit ago. The end point of that terminal side, or the arc, has a coordinate. We need to figure out the x and the y value for that coordinate. So all the angles we're going to study are going to be connected with coordinates on the circle. And the coordinate is going to be able to help you to do something with trig. What does it allow us to do? It allows us to find all 6 trig functions of an angle. So we're going to be finding trig functions based on knowing the location of the angle in the circle, specifically the location of the terminal side. And these are things, like Mr. Babb said, very important. By the time we've been doing this for a couple weeks, hopefully it becomes automatic. Like I could say to you, sine of 30, you'd know, 0.5, 1/2, automatic.
Oh, okay.
Or cosine 30, 3/2. You almost memorize them after you've used them enough. Okay, so we're going to find a coordinate, and once we find it, we're going to use the x and the y value of that coordinate to find what we call trig functions. Now, we're going to start right now just by labeling 4 coordinates that I hope you can figure out the coordinate for. They're going to be even simpler than an angle that would end up in the middle of a quadrant. They're going to be the angles that are right on the quadrants. 0, 90, 180, 270. So that's 0, 90, 180, 270. Now, what's the size of the circle again?
1.
1. So to get to 0, that's 0, 0. That's not on the circle. That's in the middle. What do you think the coordinate would be for 0 degrees? 1, 0. X value 1, y value 0. How about the coordinate for 90? 0, 1. X value 0, y value 1. You cannot switch them. They have to be 0, 1. How about 180? Yep. And 270? 0, negative 1. So those are the only 4 coordinates that we're going to work with today. I said we're going to do multiples of 30 and 45. Well, these are all multiples of 30 and 45. But they're the easiest ones we can do. We'll look at 45s that are in the middle of a quadrant in part 2. So any questions on how we found those coordinates? So now the question, well, what do you do with it? What do you do with the x value and what do you do with the y value? You plug them into different formulas. So there's 2 out of the 6 trig functions. The first 2 that are most common are sine
It's so weird seeing them with these.
and cosine. Does anybody know what the other 4 are? Sine, cosine.
I know.
Tangent.
Cotangent.
Cotangent.
Sure.
Secant
Oh,
and cosecant.
Yeah.
forgot about secant.
To calculate each one of these values, it depends on either a y value, an x value, or both. And if you're like, well, what does that even mean, to take the sine of an angle? Well, it's kind of like, what does it mean to take the log of 3? It means to take the number 3, and you're plugging it into a formula that performs an operation on it and gives you an answer. When you take the sine of an angle, you're plugging a number into the sine formula, and the sine formula is doing some arithmetic to that and giving you back an answer. What is the result of what it does? Well, it's the y value of the coordinate for that angle. If you wanted to plug an angle into the cosine formula, the result is the x value of the coordinate that represents that angle. We're only working with zeros, ones, and negative ones, so we're going to get pretty simple answers. And the tangent is when you divide the y value by the x value. So you need both. And now when you start to get into division, you have to be careful because if you ever had an x value that was 0, now you're trying to divide by 0. So tangent can have undefined values, like the tangent of 90 is undefined. Think of 90 in your head. Think of the x value. Think of the y value. And it would be 1 divided by 0. So that's undefined. Sine and cosine are never undefined. Never. You always get an answer. And those are the other three. Cosecant, secant, and cotangent. And I paired them up for a certain reason, the way I did. I want cosecant next to sine. And I wanted cosine next to secant and cotangent next to tangent.
Because they undo each other.
Because there's a connection between them. And if you know these,
Oh wait, aren't they the same?
they're not the same.
Those are the opposite as sorry.
They're what? And when you raise something to the -1, what does that basically do?
1 over the number. 1 over your
1 over, which basically in a single simple word means to flip it. Flip. Okay, just flip it. So, well, you guys say, well, how do you flip y? Well, think of it as y over 1. So what do you get when you flip y over 1? 1 over y. And what do you think the secant is? 1 over x. And the cotangent? X over y. So you need to know those formulas. Sine is y, cosine is x, tangent is y over x. If you know those three, and then you remember to get the other three, you flip them, then you don't really have to memorize the other three. Generally, when you write a trig function, they all have a 3-letter abbreviation. That's what we'll be seeing pretty much for the rest of the time we do trig.
Alright, so both tangent and cotangent can be undefined. Wait, okay.
Yes.
Can all of them except sine and cosine be undefined?
Yes.
I see.
Every single one of them, there is a way to make the other 4 undefined somehow. So the 3-letter abbreviations for each trig function are generally the first 3 letters of the name, except in the case of cosecant, we've already used COS somewhere else. So then they just go by syllables, cosecant. But everything else is just the first 3 letters. And all of these trig functions take an angle as the argument. So when you take the sine of something, the something you plug in is an angle. 70 degrees, 206 degrees, 5 pi radians. Whatever it is, it's an angle. The answer that you get is just a number. So like if I do the sine of 30, sine 30, I get 0.5. What's the unit on 0.5? There is no unit. It's just the number 0.5. What's the unit on the 30 here? Well, that was degrees. So now it starts to be a little bit important whether our calculator is in radians or degrees. Because if I wanted to take the sine of 30, which eventually you should just do in your head, but if you typed it in, and you wanted the sine of 30 degrees, but your calculator is in radians, this is giving you the sine of 30 radians, which is not the same thing. So it starts to become important to know what mode you're in. Any questions about those formulas? So the 4 angles that we're focusing on right now, and the only ones we're going to do today, are called the quadrantal angles. Quadrant. The reason they're called that is because they are the angles that land on the axis. X, positive y, negative x, negative y. So if I ask you to do a problem like that, find the 6 trig functions of pi. That means I want to know the sine, the cosine, the tangent, the cosecant, the secant, and the cotangent. So how do you do it? Yeah, you're gonna have to know the unit circle because it won't help you with what I'm gonna ask. I'm gonna ask you for the coordinate.
Oh, yeah.
And that's the first step. Find the coordinate. Now, sometimes they'll give you the coordinate. So if they give it to you, then great. You don't have to worry about finding it. But that's the first. Find the coordinate. And the second step is to plug in the x value or the y value into whatever it is they want to know. Generally on the test, I'll ask you for 1 trig function per problem. Like, find cosine of 180 degrees. That would be a test question. In class, we'll practice all 6. The sine, the cosine, the tangent, and so on. So we're going to use all the formulas. So for this week, the only 4 coordinates, or the only 4 angles that you have to find the coordinate for is 0, 90, 180, 270. Those are the only 4 I would ever ask you to find a coordinate for this week.
What's the formula they're talking about into? Just like whatever one pertains to the problem.
Yep, all 6 of them. We're going to do all 6. Those are your formulas. Okay. Let's look at this first one. So they gave me the coordinate, 0, 1. Does that look like a coordinate that we've discussed today?
Yes.
Yes, it is. It is an angle. Do you need to know the angle to do this problem? No. All you need to know is the coordinate. I can tell you the angle, it's 90. But does that matter? Nope. So let's start with the sine of our angle represented by this point. What's the formula for sine? It's equal to y. And what's the y in this case? 1. There's the sine of the angle represented by this point. Forget that this point is 90. You know it's 90, but forget about it. Because you're going to have no clue what this next one is. You're not going to know what angle that is. It doesn't matter what angle it is. Let's do the cosine. So whatever this angle is, we have its location. And what's the formula for the cosine? X. Done. What's the formula for tangent? Y over x. That's undefined. So whatever this angle is, if you knew it and plugged it in on the calculator, you'd get undefined. That's why I said the calculator is not going to help you because I'm giving you the coordinate. What's the trig function that you flip from sine? Sine, if you flip it, gives you the what?
Cosecant.
Cosecant. And if you flip 1, you get
1.
1. You're just taking these 3 numbers now and flipping them. What's the name of the one that you flip to get from cosine? Secant. And if you're not sure how to flip that, well, think of it as 0 over 1. That's undefined. And how about the cotangent? And what's 0 divided by 1?
0.
0. So when you flip 0, you get undefined. When you flip undefined, you get 0. That's the only one that's a little weird. 1 is the only one of two numbers you can flip and it stays the same. Does anyone know the other number you could flip and it would stay the same?
0.
No.
No, we just did that number. -1.
-1. So those are the 6
So I'll think of all the weird numbers.
trig functions for that angle. That would be 6 separate questions on a test.
Okay.
Okay, let's look at this one.
Oh. Oh.
Now, does that look like a coordinate we've talked about? No.
I don't think
It is a coordinate for something. I know what angle it is, but it doesn't matter what angle it is. All we need is the location, and that's what we have. So what's the sign of the angle represented by that location? Square root of 3 over 2. How about the cosine? 1/2. And what's the formula for tangent? Y over x. So what I do visually to imagine the tangent is I put a line, almost like I'm dividing y by x. And if I divide y by x, what happens?
just the same as multiplying by 2, isn't it?
Multiplying it by 2, right? So the 2's are going to cancel.
Yeah.
Whenever you divide fractions with the same denominator, the denominator is gone because you would normally flip and multiply. So the 2's are gone. And what are you left with?
Just sort of 3.
Just square root of 3. Okay. How about my cosecant?
2 over square root.
2 over the square root of 3. But what's wrong with that?
You have the radicals in the denominator.
Yeah, we don't want to leave the radical in the denominator. So what do you multiply by to fix it? Square root of 3. And what does that give me?
3. Oh, 1 times 2 times square root of 3, and then over 3.
Over 3. So the part of fixing the radical in the bottom, that would be more of like an algebra 2 thing, but you always have to rationalize your fraction. How about my secant?
That's just 2.
That's just 2. And how about my cotangent? What would the first step be?
Flip it.
Flip it, which would give me,
1 over square root of 3.
and fix it.
Square root of 3 over 3.
Square root of 3 over 3. Question on it? So that's one where they gave you a coordinate that maybe you don't know what the angle is, but that's okay. All you need is the coordinate. All right. What's different about this one?
It's not injury. We don't have the coordinate.
We don't have the coordinate. So in a problem like this, you need to find the coordinate first. So what I usually do in my head is I visualize the circle, and I imagine where 90 is. Where's 90 in the circle?
Straight up.
Straight up. So that means we don't go left and right, we go up. So that's 0, 1. So now, we've already done that problem.
Yeah.
So from here, see example 1a. It's the same question. The only thing you had to do was find the coordinate first. How about, what's the coordinate for 270?
0.
And now once you have your coordinate, fill in your x's and y's. How about pi? Think first, what is pi in degrees? That might make it easier. 180,
Just divide by pi and multiply.
because 2 pi is 360, so that's half. And what's the coordinate for 180? Okay, imagine your circle. 180 is halfway around. So -1, 0. And then you plug them all in. All right. Well, we just did pi. How much was pi? 180. So what's pi over 2? 90 times 7.
630.
630. Now, we talked about what happens when an angle is more than 360. It just means you went around more than once. What can you subtract from that to make it smaller? You can always add or subtract 360 from an angle to make it more manageable in your head. So that's the same as 270. And 270,
We know is
we just did. So this would be the same as example 3. So I'll just put C example 3. Now, if you got an angle that was negative, what could you add to it to make it positive?
360.
You could add 360. Yep. So, what would negative 90 be the same as?
Positive 270.
Positive 270. And that's exactly the same question we just did in example 5, which is exactly the same question we did in example 3. So sometimes a question might look a little different, but it might be exactly the same as something you've already done.
Yeah, I'm not hungry. Oh. Hold on.
That's the home. So it's 56 to 59, 70 and 71. That's the angular and linear velocity. That's on page 324. Now on 335, there's only 3 problems from the book. 1, 5, and 8. Do whatever the book says for 1, 5, and 8. But then, after you do that, I think it wants you to find the coordinate. Then I want you to take the coordinate and do the 6 trig functions for 1, 5, and 8. And do the 6 trig functions of 3 pi over 2. So find the coordinate. 2 pi, find the coordinate. And do the 6 trig functions of root 2 over 2, comma, root 2 over 2. This is not a coordinate you've probably seen. So it represents an angle, but you don't need to know what it represents. The important thing is you have the coordinate. Okay, so we could spend maybe 40 or 45 minutes going over all of that tomorrow. And that's it for material this week.